Okay, so you want to build a data center, buy some land in Northern Virginia. Pour concrete, stack thousands of servers inside, plug them into the local power grid, and watch the cash roll in every time someone streams a video, sends a text, or asks an AI a question. Here's the strange part. The world's largest technology companies are currently spending hundreds of billions of dollars building these facilities, and yet almost no one outside the industry understands what is actually happening inside them. By the end of this video, you'll know exactly why a modern data center costs more to build than a modern aircraft carrier, how a facility the size of a Walmart makes its money on something most people have never heard of called a megawatt, why the same machine that prints cash in one season can become obsolete before the concrete has even fully cured, and why the business everyone blames for your rising electricity bill is more often than not barely breaking even on the power it consumes. Data centers come in three sizes, and they are three completely different businesses. A small edge data center, the kind tucked into an industrial park to shave milliseconds off your mobile game's latency, runs you $10 to $50 million. You got a few hundred server racks, a couple of backup generators, and a local fiber connection. A real enterprise data center, the kind that handles regional traffic for a major bank or healthcare network, costs $100 to $300 million depending on redundancy and security. You need dual power feeds, massive cooling loops, and armed security guards. And then there's the project that just put data centers at the center of the global economy. In 2026, hyperscale campuses being built by companies like Microsoft, Amazon, Google, and Meta routinely exceed $1 billion to $3 billion per facility. Microsoft's planned Stargate supercomputer data center project backed by OpenAI is projected to cost upwards of $100 billion across its full life cycle. That headline number isn't just a building, it's a small city built entirely for silicon. Why did it cost so much? The building was never the hard part. The power was. A modern hyperscale data center consumes as much electricity as a small town of 100,000 people. We aren't measuring these facilities by square footage anymore. We measure them by megawatts. A standard facility running 30 to 100 megawatts requires a dedicated electrical substation built right next to it, pulling power straight from high voltage transmission lines. The rule of thumb in this industry for the last several decades has been simple. It's easier to find $1 billion than it is to find 100 megawatts of unallocated grid capacity anywhere near a major population center. So that's exactly why data center developers are now fighting, with utility companies buying failing coal plants and investing directly in nuclear energy to keep their servers breathing. Now, the question that actually matters: where does the money come from? It's not the internet traffic, it's the capacity. The industry calls it wholesale colocation and hyperscale leasing. And once you understand it, every headline about the AI boom makes a different kind of sense. Here's the idea. A data center developer builds the shell, installs the power distribution units, lays the liquid cooling pipes, and runs the fiber. Then they lease that space out to tenants who bring in their own server racks. The standard way the industry measures this is cost per kilowatt per month. If a tenant leases 1 megawatt of critical IT load, they aren't just paying for electricity. They are paying a bundled rate for the space, the cooling, the security, and the guaranteed uptime. A healthy wholesale lease historically runs anywhere from $100 to $200 per kilowatt per month, depending on the market and cooling technology. During supply shocks like the massive AI-driven GPU shortages and power crunches of 2024 to 2026, prime data center space with liquid cooling capability has seen lease rates skyrocket. And this is the part that breaks people's brains. A data center operator doesn't actually want cheap power. They want stable power, paired with a tenant locked into a 15-year triple net lease, where the tenant pays for every kilowatt hour consumed, plus the infrastructure markup. When local electricity rates spike because of grid strain, the data center's wholesale contracts usually include pass-through clauses. The tenant pays the utility bill while the operator collects their fixed margin on the infrastructure. Earlier this year, when surging AI workloads pushed power demands to unprecedented highs in Northern Virginia's data center alley, operators running on long-term power purchase agreements saw their margins widen sharply for reasons that had nothing to do with how efficiently their individual servers were running. That's the entire business model in one sentence. A data center is not in the business of computing. It's in the business of real estate, power distribution, and thermal management. And those three variables can move for reasons completely outside of the operator's control. Now, the part nobody puts in headlines. Data centers don't just hold one type of computer. They host thousands of distinct systems simultaneously. And the profitability of the whole operation depends on getting the thermal mix right. Out of one server hall, a data center is pulling standard cloud computing servers, high-density AI training clusters packed with liquid-cooled NVIDIA Blackwell GPUs, legacy enterprise mainframes, and massive storage arrays all at once, all generating different amounts of heat, all demanding different levels of power reliability. AI workloads peak unpredictably whenever a massive model is being trained or a viral feature drops. That sudden compute surge can spike power densities from 10 kilowatts per rack to over 100 kilowatts per rack almost overnight. Standard air cooling cannot handle 100 kilowatts in a single rack. The chips simply melt. This means a data center is essentially running 5 different thermal engineering environments inside one building, managing liquid cooling loops, rear door heat exchangers, and massive chiller plants all day, every day, just to protect the hardware from self-destructing. And operators don't just lease space at whatever the market gives them that day. They lock in long-term contracts. A developer can secure power capacity and lease agreements years in advance, guaranteeing revenue before the first server is even uncrated. In one real industry example, a hyperscale developer locked in a 15-year lease with a major cloud provider at over $150 per kilowatt per month, guaranteeing hundreds of millions in baseline revenue. Regardless of where macroeconomic tech spending moved between now and then, it's less like running a traditional office building and more like running a high-security power plant that happens to store the digital memory of global civilization. Here's the part that explains why your internet latency has almost nothing to do with the router in your living room and everything to do with which geographical market your favorite app's data center happens to sit near. Northern Virginia is the center of the global internet. Ashburn, Virginia alone processes an estimated 70% of the world's internet traffic every single day, tightly clustered, feeding massive fiber optic backbones that crisscross the entire planet. If one major substation there goes down, millions of streaming sessions, financial trades, and cloud databases are disrupted. The region is in effect one giant shared digital nervous system. Other markets don't have that scale. Secondary markets like Phoenix, Dallas, or Dublin are growing rapidly, but they face their own constraints, particularly water and power. And right now, utility companies are pushing back. Local governments in parts of Virginia and Ireland are placing temporary moratoriums on new data center hookups because the local grid simply cannot handle another megawatt together. Those local restrictions represent a massive bottleneck for an industry trying to expand as fast as artificial intelligence can demand. Economists and energy analysts model what happens next and project that powering these new facilities could raise consumer electricity rates across entire states. Industry groups point to the multi-million-dollar tax revenues data centers bring to local school districts as the trade-off. State officials and utility regulators dispute how much of the grid strain that actually explains, versus how much comes from the sheer velocity of the AI boom. Either way, the lesson for anyone thinking about this business is the same. A data center isn't just a warehouse full of computers. It is critical national infrastructure, and when critical infrastructure strains the local grid, the math doesn't get redistributed evenly across the economy. It gets dumped entirely on whoever shares a transformer with the building that just plugged in. So, with guaranteed demand locked in, long-term leases, and a business, nobody else is allowed to easily build because of power scarcity. Why are data centers actually one of the most capital-intensive and risky parts of the entire tech ecosystem right now? Two forces are squeezing this business at the same time, and almost every major operator in the world is dealing with both. Force 1, the technology inside the building, has a shelf life that borders on terrifying. According to industry analysis, enterprise server hardware depreciates aggressively, often becoming obsolete within 3 to 5 years as more energy-efficient chips take over. But the building itself, the concrete shell, the generators, the chillers, the heavy-duty electrical bus bars, has to last for 30 years to pay back its construction debt. This creates a structural mismatch. You're building a 30-year real estate asset for a 5-year silicon cycle. If you design a data center optimized for traditional air-cooled CPU servers, and the market suddenly shifts entirely to high-density liquid-cooled AI GPUs, your multi-million-dollar facility can become functionally obsolete before you've even finished paying off the construction loan. We are watching this happen in real time. Older data centers built just a decade ago with low power density limits cannot support modern AI clusters. They are being retrofitted at immense cost or left behind as digital ghost towns, while hyperscalers build entirely new campuses designed from scratch for liquid cooling. Force 2, the thermodynamics can kill the facility, and when they do, it's catastrophic. On a hot summer afternoon, if a chiller plant fails and backup generators stumble during a grid brownout, the internal temperature of a high-density server hall can rise to critical levels in a matter of minutes. When silicon overheats, servers automatically shut down to prevent permanent damage, but a sudden mass shutdown across 50,000 servers can cause data corruption, drop millions of active user sessions, and trigger cascading software failures globally. Property damage from a single major fire or electrical arc flash in a high-voltage substation can run into the tens of millions of dollars, completely independent of the lost revenue from downtime. The financial penalties for breaching a service-level agreement, an SLA guaranteeing 99.999% uptime, known in the industry as 5 nines, can wipe out a month's profit in a single afternoon. 5 nines means your data center is allowed a total of only 5 minutes and 26 seconds of unscheduled downtime per year. Exceed that, and you owe your enterprise tenants heavy financial compensation. One bad switchgear failure, a blown transformer, or a software glitch in the building management system, and millions of dollars in penalties are triggered. That's the liability sitting underneath every single data center operator every single day. It operates. Step back for a second. A data center is a paradox, the same way a modern utility is. It sits at the center of a product everyone on Earth uses every single second. With unprecedented demand on its side, nobody's allowed to easily build a new competitor without billions of dollars and years of grid negotiations, and it still runs on margins. So complex and capital intensive that a miscalculation in power forecasting or cooling design can wipe out a developer's equity. The electricity coming in is high voltage, the data coming out is global. You're not really running a real estate business. You're managing an immense thermodynamic balancing act at scale and getting paid for the reliability of the uptime you provide. 2 scenarios. Real numbers. Scenario 1. A small regional edge data center. Modest processing capacity. Standard air cooling. Maybe a few megawatts of total load. Initial cost in the tens of millions. In a strong enterprise demand environment, you can clear a steady profit. In a weak one, you're running at tight margins trying to compete with hyperscale cloud providers, who can undercut your pricing entirely due to economies of scale. This is the entry-level version of the business. It lives or dies entirely on regional enterprise clients with zero room for error. Scenario 2. A Northern Virginia hyperscale mega campus, multi-billion-dollar build, hundreds of megawatts of capacity, advanced liquid-to-air cooling systems, dedicated electrical substations. At a healthy $150 per kilowatt per month lease rate, a 100 megawatt facility is generating tens of millions in monthly revenue before operating costs. At a weak power availability or cooling failure, the same facility could face massive regulatory fines, expensive emergency retrofits, and severe SLA penalties. Same building, same crew, same fiber, coming in the front gate. The difference between a billion-dollar success story and a capital expenditure nightmare isn't anything the operator did day to day. It's a grid capacity limit set by a local utility board that the operator has almost no control over. That's why every serious player in the business is now securing their own power generation. In 2024, tech giants and data center developers began making headlines by partnering with nuclear energy providers. Microsoft famously reached an agreement to help restart a unit at 3 Mile Island to secure dedicated carbon-free nuclear power exclusively for its data center operations. Amazon bought a nuclear-powered data center campus outright in Pennsylvania. For half a century, Data center operators just plugged into whatever wall socket the local utility provided. The regulatory and energy cost of a hyperscale campus simply grew too high for the public grid to bear alone. Then came the AI revolution, and that passive model broke entirely. Ground gets broken this year on campuses, engineered specifically to consume massive blocks of baseload nuclear or geothermal energy. Instead of relying on the strained fossil fuel grids surrounding major cities, that is the actual economics of owning a data center. It's not a business about computers. It's a business about power, heat, and space. Sitting inside a building so expensive and so energy hungry that almost nobody can build a new one without a multi-billion-dollar balance sheet. In a network so concentrated that losing just one key region can disrupt the digital infrastructure of entire nations who never thought about where their data actually lived. Build it right, and you own one of the few machines on Earth that the entire modern global economy cannot function without. Build it anywhere else without guaranteed power and cooling conditions, and you'll find out exactly how fast a multi-million-dollar server hall can become obsolete. Usually in the same week, the market decides to ask why your uptime slipped.